Good day everyone and welcome to our first lesson. In this video, we will be discussing wastewater treatment technology. We will start with a recap of the Republic Act 9275 or the Clean Water Act of the Philippines, and then we will talk about the entire conventional water treatment paradigm, and then we will talk about some emerging technologies in wastewater. Let's begin with RA 9275 or the Clean Water Act of 2004. This provides the legal framework for the maintenance of effluent streams within a set of standards. Here are some salient points of RA 9275 and its implementing rules and regulations. That is the DENR Administrative Order 2005-10. First, we have the establishment of a wastewater charge system and application for discharge permits. Next, we have tax incentives for those adopting new technologies for wastewater treatments. We also have corresponding penalties for violations of the law. And finally, we have the framework for the wastewater effluent standards. This has been updated through the virtue of Department Administrative Order 2016-08. We will be discussing the wastewater effluent standards in detail later. Let's first talk about the discharge permit. The discharge permit is granted to establishments that have applied for discharge of their treated wastewater. Basically, all establishments that release wastewater into Philippine waters upon treatment require a discharge permit. Facilities that do not treat their own wastewater but instead relegate the task to a centralized wastewater treatment facility are exempted from obtaining a discharge permit. From what we have here, all establishments that treat wastewater, either it's their own or it's from somebody else, needs to secure a discharge permit. Effluent trading is allowed within the same management area. This is applied to industrial ecoparks, wherein the wastewater of one process or of one establishment can be a useful raw material for another establishment. Therefore, they can establish an effluent trading wherein the establishments that disposes of the wastewater can save some money because they are avoiding the treatment. Okay, this is allowed for industrial ecoparks. The discharge permits are valid for 5 years and are renewable. Annual fees are collected depending on the volumetric rate of discharge. So, of course, a higher volumetric rate of discharge would incur a higher annual fee. The details for the application for a discharge permits are given in the website of DENR. Now let's talk about the DENR Administrative Order 2016-08. This document includes the updated classifications of bodies of water as well as the limits for the primary and secondary components of effluent wastewater. These are the classifications of bodies of water based on the intended use. On this first table, we have classifications of fresh water. Let us start with the cleanest at the very top. We have Class AA. Class AA is Public Water Supply Class 1. This is a source of water that only needs disinfection to meet the Philippine national standards for drinking water, meaning that it is already potable after only disinfection. Okay? That implies that Class AA water is pristine. It is very clean. It has no detectable amounts of BOD, nitrates, and other substances. We will discuss this more later. Next classification, we have Class A. This is Public Water Supply Class 2. These are the sources of raw water that needs full water treatment to meet the Philippine National Standard for drinking water. These classes of water are the sources for our water concessionaires like Maynilad and Manila Water. Normally, these are from dams, rivers, or reservoirs that are exposed to minimum amounts of pollution. They are still relatively clean, although they need the entire water treatment to meet the standards of our drinking water. Next, for Class B, these are recreational waters Class 1. These are for primary contact recreation like swimming and water sports. Class C is fishery waters for propagation of fishes, as well as recreational waters Class 2. This is for non-contact recreation like fishing and boating. Class C is also the classification for agricultural water and water used for irrigation. And finally, Class D, or the lowest class of fresh water, are navigable waters. Now, the only thing that classifies waters based on this classification is their cleanliness or the amount of pollutants and other organic substances present in the water. Also, this classification is useful for us to determine what are the maximum amounts of BOD, nitrate, and other wastewater quality parameters that are needed for the discharge on these bodies of water. We will go back to this classification later in the effluent standards. In this next table, we have the classifications for salt water. So the previous table is intended for fresh water and this is for salt water. Notice that there is no class SAA because there is no potable salt water. So the highest class for salt water is class SA. These are protected waters. Normally, these are breeding grounds of important fish species as well as estuaries. This is also classified as fishery water class 1 for direct shellfish harvesting. So this is the cleanest class of salt water. Next, we have class SB. This is fishery water class 2 for commercial raising of fish and shellfish. This is normally seen in areas of saltwater wherein there are fish cages that are intended for commercial raising of important fish species. In the Philippines, that is bangus or saltwater tilapia. Class SB is also designated for tourist zones and recreational waters class 1. This is for primary contact recreation like swimming and water sports. Next classification, we have class SC. These are fishery water class 3 for sustenance fishing, or this is for small scale fishing, and also recreational waters class 2 for non-contact recreation like boating and fishing. And finally, we have class SD, or the lowest classification of saltwater. Those are navigable waters. Shown in this table are the effluent standards that are needed to be met for the discharge of treated wastewater. Treated wastewater that will be discharged onto a body of water needs to have primary property concentrations within the limits set by Dow 2016-08. And these are the primary parameters. All of these parameters are required to be analyzed for those who will be discharging their treated effluents into bodies of water. Notice that we have here the water body classifications from class AA, A, B, C, D, SA, SB, SC, and SD. Also, notice that for the highest quality of fresh water, that is class AA or potable water after disinfection, all of the parameters should have no detection allowed or NDA. Okay? That means that the water should be very clean before the disposal in bodies of water. However, in a typical wastewater treatment plant, this is often very difficult to achieve and is very costly and it's not cost effective. Therefore, some treatment plants could choose to release their effluent in other classifications of water bodies, such as Class C or Class D for freshwater and Class SC and SD for saltwater. You would also notice that, for example, for BOD or biochemical oxygen demand, the maximum amount increases with regards to the water body classification. Let's say, for example, for Class D or for navigable freshwater, the maximum amount of BOD discharged is 120 milligrams per liter. That is higher in comparison with Class B, which is intended for primary contact recreation, with a lower maximum amount of BOD discharge, that is 30 milligrams per liter. This full table is available online. You just have to download a copy of Dow 2016-08. Time and time again, we will go back to this table whenever we are discussing effluent standards. If you notice with the previous table, the maximum amount of BOD in the effluent stream is quite low. And that is unfair for those whose influence BOD are very high. That is because if you have a very high amount of influent BOD, it would be very costly or it would be very difficult process-wise for you to meet the same regulatory requirements as that of those who are treating low BOD waters. Therefore, we have here exemptions for effluent BOD given to those dealing with strong wastewater or those with an influent BOD greater than 3,000 milligrams per liter. The reason for this is wastewater treatment becomes more disproportionately costly as the influent BOD increases if we are trying to achieve the same BOD removal efficiency as low BOD wastewaters. For example, if your influence BOD is greater than 3,000 milligrams per liter to less than 6,500 milligrams per liter, if you are disposing that into Class C waters, you're only required to keep your influence to within 100 milligrams per liter of BOD. Okay, and the maximum limit for the concentration in the discharge increases with increasing amount of influence BOD. Let us now discuss the characteristics of domestic wastewater. That is because a large portion of the wastewater generated every day comes from residential areas, and our wastewater is a large part of municipal wastewater. Whenever we talk about wastewater treatment, the first thing that comes into mind is actually the treatment of domestic wastewater. That is because that is the most common type of wastewater being treated and that is coming from residential and commercial areas. We also have other types of wastewaters, such as those coming from industries, and those are very variable in composition depending on the nature of the industry. And we will discuss those later. Shown here are the average parameters for average strength municipal wastewaters. We have BOD of around 200 milligrams per liter. We have suspended solids of around 240 milligrams per liter, although of course this could fluctuate. It could be higher or it could be lower. We have coliform counts or bacterial count of around 3 million coliform forming units per 100 milliliters. Total nitrogen of around 35 milligrams per liter and total phosphorus of around 10 milligrams per liter. So these representative values of the properties of municipal wastewater is very useful for design considerations. Let's say, for example, we are designing a new municipal wastewater treatment plant. Our starting point could be these average properties. Municipal wastewater is commonly brown to gray in its appearance, and raw wastewater has a strong smell if it is truly raw wastewater. Okay? The smell is greatly reduced after the secondary treatments or the biological treatment. Mainly, the smell is coming from the volatile substances that are released from the decay of the raw wastewater. For municipal wastewater, our main parameters for concern are BOD or COD, nutrients, and microorganisms. That is because these are the properties that are of highest concentrations in municipal wastewater. And of course, the different parts of the conventional wastewater treatment system addresses all of these parameters in different stages of the treatment. Since we are now talking about BOD, let us further discuss this common wastewater parameter. So BOD, or biochemical oxygen demand, is the amount of dissolved oxygen needed by microorganisms to consume the organic load of the wastewater. In the conventional wastewater treatment system, we are highly reliant on heterotrophic bacteria to consume the organic matter in the wastewater and turn it into carbon dioxide and water. And that process cleans our wastewater. That's why the measurement of the biochemical oxygen demand is an important parameter in wastewater treatment. A high BOD value means that there are plenty of organic material in the wastewater. So the higher the BOD value, the higher your concentration of organic materials is. For reference or for scale, we have here some sample values of BOD. For a clean river, you have a BOD of 2 milligrams per liter or even lower. Pasig River has a BOD of 35 milligrams per liter. This is on average. The average municipal wastewater, as discussed earlier, has an average BOD of around 200 milligrams per liter. This is the wastewater coming from our houses, from our toilets, and from our sinks. Piggery wastewater has a BOD of 3,300 milligrams per liter. This is very high and very problematic. That's because this wastewater is oftentimes concentrated and contains large amounts of pig manure and uneaten feeds. And finally, we have distillery wastewater with an average BOD of around 44,000 milligrams per liter. So to scale, a very clean river has a very low amount of BOD. Mostly, this is just coming from the decay of leaves, dead fish, and other decaying organic matter present in the river. In contrast, we have distillery wastewater with a very high amount of BOD. Imagine what will happen to the river if we dump distillery wastewater into it. The BOD would immediately go up, and the river would need more oxygen for the bacteria to consume that organic matter. And since the decomposition of organic matter uses oxygen, we are actually in danger of utilizing the dissolved oxygen of bodies of water, and that leads to suffocation of aquatic life. That is what happens during fish kills. Whenever there is an excess amount of organic water in bodies of water, and then bacteria are actively metabolizing that organic matter, they are using the dissolved oxygen in the body of water. And if this happens fast enough, the fishes and other aquatic life are actually suffocated to death because of the lack of the dissolved oxygen. This is the typical way on how we measure the BOD value of a sample of wastewater. BOD is determined by taking dissolved oxygen measurements for a water sample seeded with microorganisms that degrade organic waste. Our formula is BOD5, or the BOD measured after 5 days is the dissolved oxygen initial minus the final dissolved oxygen, or the dissolved oxygen after 5 days, divided by the dilution factor for the wastewater. Those measurements are normally carried out in these types of bottles wherein a sample wastewater is diluted and seeded with microorganisms. It's capped tightly, and then the dissolved oxygen is monitored at the start of the experiment and after 5 days. BOD5 is the standard measure of BOD used by laboratories. So as you can imagine, the measurement of a BOD sample takes around 5 days, and that is mostly due to the slow nature of bacterial action. BODU, or the ultimate BOD, is the maximum BOD of a sample, and it's usually taken as BOD20, or the BOD measurements at the 20th day of the experiment. Let's have a brief discussion on BOD kinetics, or what really happens with the consumption of the BOD. We have here two graphs on the figure here. The figure at the top is the CBOD exerted. CBOD means carbonaceous biochemical oxygen demand, meaning the BOD coming from carbon sources only. The exerted BOD increases with respect to time. That is because as time progresses, more and more oxygen is being consumed by the degradation of the BOD. In contrast, the graph at the bottom shows you the CBOD remaining as a function of time. As the bacteria degrades your carbonaceous biochemical oxygen demand, the concentration of organic matter decreases and decreases. So the BOD exerted and the BOD remaining are inverses of each other. Our formula for the BOD remaining is L sub T, or the BOD remaining at any time T, is equal to the ultimate BOD, or the BOD at the beginning, multiplied by e raised to negative KL times time. KL is what we call the deoxygenation constant. This is the specific reaction rate constant used to characterize how fast are we consuming the oxygen in the water. Next formula, we have the BOD exerted, or Y. The BOD exerted at any time T is equal to the ultimate BOD minus the BOD remaining at any time T. So you can imagine that as time progresses, the remaining BOD decreases and the BOD exerted increases. Combining these two equations, we have the BOD exerted at any time T, that is Y sub T, is equal to the ultimate BOD times 1 minus e raised to negative KL times T. Y sub T here can be substituted to become BOD5, or the BOD after 5 days, if we substitute time as 5. And L sub O is the BOD20, or the ultimate BOD. As stated earlier, the BOD remaining gives a measure of the remaining degradable organic compounds in the water sample. That's why as time progresses, the remaining BOD decreases. Next, the BOD exerted gives the amount of dissolved oxygen needed by bacteria to consume the organic compounds in the water sample. As time increases, the BOD exerted increases. That's because the bacteria need more and more oxygen to degrade the organic compounds. Also, as mentioned earlier, K sub L is the deoxygenation constant, which has a unit of per day. The value of the deoxygenation constant depends on the temperature. Of course, a higher temperature would implicate a higher degree of bacterial action, so it is faster in degrading the BOD. Our formula is KL is equal to KL20, or the value of the constant at 20 degrees Celsius, times theta raised to T minus 20, wherein T is the temperature in degrees Celsius. For the value of the deoxygenation constant at 20 degrees Celsius, that is 0.1 per day for polluted water or the standard domestic wastewater, or the value 0.23 per day for sewage water. These are the values of theta, and the values of theta are dependent to the temperature range being considered. Just keep in mind this formula used for the calculation of BOD. Now, regarding the release of treated effluent to a body of water, let us consider the release of treated effluents to a river. Assume for a moment that the treated wastewater has a remaining BOD of 50 milligrams per liter. If we release that wastewater to a river, let's say for example, we are releasing the wastewater at this point here, at distance is equal to 0, or at the premises of the wastewater treatment plant. What happens is we are increasing the BOD of the river, and that means that the river needs more oxygen for it to be able to degrade the organic matter present in the effluent. What would then happen is, if we assume the flow of the river to be from left to right direction, as the effluent released is being transported down the river, it consumes more and more oxygen. That's why the dissolved oxygen of the river is decreasing. After some time, we would be reaching a critical point or a minimum amount of dissolved oxygen, wherein it is at this point that the BOD in the wastewater has already been consumed. From this point onwards, the dissolved oxygen slowly increases because of the reoxygenation properties of the river. That could be because of turbulence, of surface agitation, or of other factors. Therefore, as the reoxygenation becomes faster than deoxygenation, the dissolved oxygen levels of the river are restored to their original value or near the original value. This DO Sag curve is very important because this tells us at which point of the river we will have the minimum dissolved oxygen. If for some reason we have calculated that the minimum dissolved oxygen is below 2 parts per million or below 2 milligrams per liter, that would be very dangerous to the aquatic life present in the river. The DO Sag curve then becomes a very important tool for us to plan how much wastewater can we release to a river without affecting aquatic life, or what is the maximum BOD that we can release into the river such that the river can handle the influx in the organic waste. Okay? For design purposes, we don't want the critical point or the minimum dissolved oxygen to go beyond 5 or 4 milligrams per liter. It is at that point that some aquatic life, particularly the sensitive species, would start having difficulty to breathe and they can start dying. This DO-SAG curve is described by the Streeter-Phelps equation. That equation can help you determine the value of the minimum dissolved oxygen and the position of the critical point. And that is a very important tool for planning the release of effluent. After discussing BOD, let's now discuss COD or chemical oxygen demand. Now, I have mentioned earlier that the measurement of BOD takes at least 5 days because that is the standard. An alternative way of measuring the amount of oxygen needed to degrade organic compounds is by using strong oxidizing agents. This alternative is the chemical oxygen demand. COD is a faster way of measuring the organic load of a water sample. If BOD5 needs at least 5 days for the measurements of the BOD, COD only needs around 2 hours for the digestion and for the measurement itself. The general process is you prepare the sample, that is, you will be adding potassium dichromate, a strong oxidizing agent, plus sulfuric acid and other catalysts to your sample wastewater, and then you digest that at 140 degrees Celsius 1 hour. After that digestion is complete, you simply subject your samples for spectrophotometric measurements. You are either measuring the excess concentration of the dichromate ion or any other colored substance that would indicate the COD value of the wastewater sample. However, COD measurements are almost always higher than BOD readings and could include significant error depending on the composition of the water sample. Since COD involves the use of a strong oxidizing agent to oxidize organic matter in your wastewater sample, it could also oxidize inorganic species like chloride, sulfate, and other metal ions. That means that depending on the amount of inorganic anions or cations in your wastewater sample, you could get a disproportionately high value of COD compared to the BOD. But generally, for a specific type of wastewater, we can draw specific relationships between the COD and the BOD such that we can get away by just measuring the COD and then just converting it to a theoretical value of BOD based on the established relationship. Another parameter that deserves our attention in wastewater treatments are nutrients, specifically nitrogen and phosphorus. Nitrogen and phosphorus are major nutrients that enable the growth of plants, but plants are not the only biological species that can capitalize on the amount of nitrogen and phosphorus present in a body of water. When nitrogen and phosphorus are present in excess quantities in bodies of water, this can cause eutrophication or the rapid growth of algae, often leading to the suffocation of aquatic life. This is what we characterize as the water turning green or brown or reddish. That is because of the very rapid growth of microalgae species. They rapidly grow because of the abundance of the nutrients present in the water. And those microalgae species generate oxygen during photosynthesis, that is during daytime, while during nighttime, they are actually consuming some oxygen that are used for respiration. And if you have a critical concentration of microalgae in water, when they respire by night, they could deprive the body of water with dissolved oxygen. And a lower value of dissolved oxygen could be very dangerous to the other types of aquatic life such as fishes, shellfish, and other aquatic plants. That condition is called eutrophication, and this is very disastrous for aquatic ecosystems. Nitrogen in water can be present as ammonium, nitrite, or nitrates. Free ammonia and nitrites are highly toxic even though for concentrations as little as 0.5 ppm. But if we convert nitrites and ammonium into nitrates, we can get away with higher concentrations without endangering aquatic life. However, the problem with nitrate is it's very stable in the environments and it is still a contributor to eutrophication. In general, we do not want nitrogen compounds being disposed into our bodies of water. Phosphorus is mainly present in water as phosphates or as organic phosphorus that is bound in some organic matter. Phosphorus is often more easier to remove in water compared to nitrogen. That's because nitrate is highly soluble, while phosphorus can be largely found as part of the solids with a minimal amount of dissolved phosphates in water. These are sample pictures showing you the dangers of eutrophication. So all of the green patches you see here in this natural body of water, this river, are all rapid growth of microalgae. These are several common discharges that trigger eutrophication and threaten surface water quality. For agricultural lands that are near a body of water, we have excess fertilizer runoff. This is the result of the indiscriminate and unplanned use of fertilizer in farmlands. The excess fertilizers are simply washed away by precipitation and are carried into surface waters. Once the excess fertilizers are in surface waters, they are very rich in nitrogen and phosphorus and they kickstart the process of eutrophication. Another common source of excess nutrients in bodies of water are untreated or poorly treated wastewater. Now that we have reviewed the common wastewater parameters that are of importance to us, let us now discuss the composition of wastewaters of some common industries. This is alongside our knowledge of the common composition of municipal wastewater. It is important to recognize the common values of the parameters of wastewaters of some common industries because the knowledge of such would help in the design of an appropriate wastewater treatment facility that is specifically designed for that industry. Let us start with agricultural processing wastewater. This includes a multitude of different industries that involve the production and processing of agricultural products. We have here some examples like food processing, palm oil mill, dairy, winery, cheese dairy, olive mill, etc. All of these industries utilize an input from the agricultural sector and their outputs are important consumer products. The wastewater of these facilities typically contain elevated levels of BOD, suspended solids, and color. Let's take the example of the production of cheese. So we have here cheese dairy. The wastewater from cheese production is mainly coming from the whey, or that is the protein solution that is separated from the curds of the cheese after the curdling process. That wastewater is very high in organic matter. As stated by the values of COD, we have here a range between 23,000 to 40,000 milligrams per liter for the COD. In addition, the wastewater of this industry is also high in phosphorus and nitrogen. We have here total phosphorus and total nitrogen. The total nitrogen is typically high because the wastewater contains whey, which is a high protein compound. For these types of wastewaters, the treatment is typically done in-house. That is because the very high amount of BOD might be inappropriate for treatment for a typical municipal wastewater treatment plant. It would either be very expensive for the agricultural processing industry to pay the municipal wastewater treatment facility to treat their wastewater, or the municipal wastewater facility might refuse these types of wastewaters because the treatment process could vary significantly. Next, we have laundry wastewater. Laundry wastewater comes from the washing and rinsing of our clothes. Laundry wastewater typically contains elevated levels of nutrients such as nitrogen, phosphorus, and sulfur. These are mainly coming from the surfactants or some of the builders used in the manufacture of the detergents. Although in recent years, some of the new detergents are lower in phosphorus content. Another typical content of laundry wastewater are textile dyes, and these are the dyes used to color our clothes. These textile dyes often persist in the environments and are very difficult to degrade. Also, in some types of laundry wastewater, wash water is differentiated from rinse water. Wash water contains a higher concentration of the surfactants or the detergent itself, as well as a higher concentration of dirts, fat, oils, and grease coming from the dirty clothes. Rinse water is a milder version of the wash water because the rinse water is much more diluted. Although in most cases, the wash water is simply mixed with the rinse water such that the concentration of the wash water will be diluted. Shown in the table here are some representative values of the wastewater parameters of laundry wastewater. You can see that we have a relatively high BOD, that is 484 milligrams per liter. We also have high amounts of phosphate, that is 64.76 milligrams per liter. We also have appreciable concentrations of some of the common ions as well as a high value of the turbidity. So if we are designing a treatment plant to treat laundry wastewater, that treatment plant would focus on decreasing the amount of organic content and also decreasing the amount of phosphorus and other nutrients. Next, we have scrubber wastewater. Scrubber wastewater comes from power plants, typically those that use coal as their source of energy. Coal-fired power plants typically have a wet scrubber that removes sulfur dioxide from the flue gas. This mainly involves contacting the flue gas with a slurry of calcium oxide or other absorbents for SO2. This is to prevent the release of sulfur dioxide to the air, which causes acid rain. However, this scrubbing process obviously generates wastewater, and the wastewater generated is called flue gas desulfurization wastewater and contains substantial amounts of metals and anions, as shown in this representative table here. Most of the metals and suspended particles come from the combustion of coal. It is no secret to us that the combustion of coal could release particles of metals or other non-combustibles to the atmosphere, and those are being captured by the scrubber. As such, if you take a look at the composition of the wastewater here, you would see elevated levels of almost all of the metals. For example, we have a high concentration of iron, zinc, nickel, lead, a high value of conductivity representing all of the other ions, as well as high concentrations of the anions, chloride, sulfates, and nitrates. The treatment of this wastewater would then involve transferring all of these metals and all of these anions in the sludge and then disposing of the sludge. Next, let us discuss mine tailings. Mine tailings are a special type of wastewater because these are not normally being treated. Mine tailings are notoriously difficult to handle because of the large amounts of metal present. Mine tailings are a byproduct of the refining process of ores. And because they are very difficult to treat, most mine tailings are not treated and are instead concentrated and stored. If you take a look at the typical composition of mine tailings, you would understand why mine tailings often are not treated. You would see that we have a very high concentration of silicon, aluminum, calcium, potassium, magnesium, manganese, all of which are commonly present in rocks and soil. But you also have elevated concentrations of heavy metals such as arsenic, cadmium, copper, lead, and zinc. The treatment of these types of wastewater would be very costly. They are not cost effective. That's why instead of treating the mine tailings, they are simply stored, dewatered, and are disposed properly. It is common to see mine tailings that are stored in this kind of manner here. They are simply kept in open ponds wherein they are allowed to dry. And when they are dried to a sufficiently low amount of water, we can simply store them in areas wherein they will not be easily picked up by water or air. Basically, we are immobilizing the metals present in mine tailings. Finally, we have metal finishing and electroplating wastewater. Metal finishing is the cleaning of metal surfaces to prepare it for surface treatment. Surface treatments could involve painting, electroplating, or finishing with a polymer coating. Electroplating is the electrolytic deposition of metal ions onto a surface. Basically, we are using electricity to convert metal ions to metal particles and then deposit them to a conductive surface. Since the nature of this industry is to contain metal ions in water prior to electroplating, metal ions are the primary causes of concern for these types of wastewater. If we take a look at some representative compositions of metallic ions in such types of wastewaters, you would see elevated levels of iron, copper, nickel, and aluminum, all of which would be very dangerous if we release them as raw, untreated water. And with that, we are now ready to move on to wastewater treatment technologies. We will first be discussing about the conventional wastewater treatment system and then later move on to some of the emerging technologies for the treatment of wastewater. Let us review the conventional municipal wastewater treatment system. Majority of wastewater treatment plants follow this conventional treatment scheme of primary, secondary, tertiary, and sludge treatment. New technologies are adopted to deal with a particular substance in the raw water. So the new technologies for the treatment of wastewater are actually very dependent on the source of wastewater. Let us do a quick walkthrough of the steps for the wastewater treatment system. The raw wastewater or the influent first passes through influent screens. These influent screens remove majority of the big particles. Then it enters the grit chamber wherein majority of the grits or the fine solid particles are removed. And then it enters the primary clarifier wherein a majority of the settleable solids are removed. The effluent to that then enters the biological treatment system. Now, the influent screens, grit chamber, and primary clarifier are all part of the primary treatment system. The primary treatment system's main focus is to address the physical properties or physical parameters of the wastewater. When we enter the biological treatment part, this is where majority of the organic compound is actually removed from the wastewater. This is already part of the secondary treatment. Now we will be discussing different types of technologies for the biological treatment of wastewater. After that, it can go to either disinfection or the tertiary treatment. The tertiary treatment involves the removal of nutrients. And finally, all of the solids that were removed from the wastewater are routed into what we call the sludge treatment processes. We will be discussing the steps of the primary, secondary, tertiary, and sludge treatments in our lecture. Let's start with the first part of the process, that is screening. As mentioned earlier, this step is done to remove large particles that could damage equipment like pumps and other moving parts. Some examples of foreign particles that could be present in raw wastewater include pieces of cloth or rags, pieces of plastics, or pieces of paper that are not disintegrated by the wastewater. This screening process can be as simple as a coarse screen that is cleaned manually or an automated system that regularly withdraws the collected solids. All of the collected solids from the screening part are sent straight to the landfill. The next part for the treatment process involves grit chambers. The main function of a grit chamber is to settle dense, inorganic particles that are not removed by screening. This could involve small bits of rock, sand, and other debris. Those particles, even though they are small, can still damage pipes and pumps, which are crucial equipments in the wastewater treatment facility. For some grit chambers, they are as simple as letting the wastewater stand and then letting the grit naturally settle down. But for some grit chambers, air is also added. The flow introduced by aeration is helpful in maintaining a vortex flow, allowing grit to settle down faster. Basically, we are introducing a helical flow into a conical grit chamber, and that allows the dense particles to settle faster. Since we are on the topic of aerating the water, let us discuss flotation tanks. Flotation is the opposite of sedimentation. So basically, instead of letting the particles settle down, we are letting the particles float to the surface. In this process, less dense particles are encouraged to float to the surface for easier withdrawal. This is applicable for particles that are naturally suspended in the water and are encouraged to float by the use of small bubbles. Diffuse aeration is done in this stage. It enhances the flotation of suspended particles and small droplets of oils. Since oils and fats are typically less dense than water, they will easily flow into the surface of the wastewater if aided by aeration. Flotation tanks are mainly used for the removal of FOG, or what we call fats, oils, and grease. Flotation tanks are used for wastewaters that contain a large amount of FOG. That is because fats, oils, and grease interfere with the biological process that is in the secondary treatment part. So the removal of FOG in the influent wastewater can greatly help in increasing the efficiency of the secondary treatment process. This is an example of a flotation tank wherein air is introduced via diffusers at the bottom of the container, and that allows for the separation of oil and water. For the next part of the treatment, we have what we call equalization basins. Equalization pertains to the slowing of the flow of influent wastewater and controlling its feeding to the treatment process. Basically, equalization affords us the control over how much wastewater will we be sending into the treatment process. This is accomplished in what we call equalization basins. This is simply a buffer so that the influent wastewater can be gathered into one container, and then we can constantly supply that influence into the treatment process. If you take a look at this figure here, we have characterized the inflow to the equalization basins as fluctuating. That is, the flow rate varies with respect to time. Actually, this is the case in most wastewater treatment systems, as the amount of wastewater that comes in to a wastewater treatment facility depends on the amount of use. For example, the amount of wastewater could be higher at night, wherein most of the people are already in their houses generating wastewater. So for this variable amount of inflow, we can equalize its flow rates by the use of the equalization basin. This equalization removes the variability of flow of wastewater from the sources and supplies a constant amount to the treatment process. The treatment process benefits greatly from this equalization because then the amount of chemicals and the amount of aeration will be constant throughout the process. Next, we reach the end of the primary treatment process. The last part involves settling or sedimentation tanks. These are also called clarifiers or clarifying tanks. The primary clarifier removes most of the settleable organic matter and concentrates it as a sludge slurry. We have here an example of a sedimentation or clarifying tank. We have here a rotating arm that scrapes the sludge from the bottom of the tank. This slow steering allows majority of the settleable solids to sink down to the bottom of the container, wherein it can be obtained as concentrated sludge. That leaves us with clarified water at the top of the container, and the clarified water can be removed by decanting. This process reduces the organic load of the wastewater to save energy in aeration. Basically, we are removing some of the organic matter here that can be settled, such that the succeeding processes would have less and less organic matter to deal with. Now we are entering the secondary process or the biological process. In these types of processes, we are utilizing the action of bacteria to degrade the organic matter present in wastewater. Let us start with the so-called suspended growth bioreactors. These are also commonly known as activated sludge processes or return activated sludge process. In this process, we have a primary aeration tank wherein we are simply introducing air into the system for two reasons. First, to mix the wastewater, and second, to introduce dissolved oxygen into the process. Earlier on in this lesson, we have discussed that dissolved oxygen is very important for the degradation of organic matter. That is because the dissolved oxygen is being utilized by microorganisms to metabolize the organic wastes. In the return activated sludge process, after a set amount of time in the aeration tank, the wastewater now enters the secondary clarifier wherein most of the sludge is settled down, and then the clear water is then sent to the next steps of the process. This settled sludge in the secondary clarifier is actually very rich in microfauna. This microfauna-rich sludge is recycled back to the influents here in the aeration tank to enrich its microorganism loading. Basically, we want to inoculate the raw wastewater with the microorganisms coming from the secondary clarifier. That gives our raw wastewater a starting boost to the population of the microorganisms, which helps degrade the organic compounds faster. Okay? But please keep in mind that not all of the sludge is recycled back to the aeration tank, just a small portion of it. Majority of the settled sludge is removed and is sent to the sludge processing. That ensures that we are not adding too much organic compound into our influent wastewater. We just want to add an initial spike of microorganisms. And by the way, these are called suspended growth bioreactors because the bacteria are residing at the surface of the solids. That is, the bacteria are colonizing the surfaces of the solids present in the wastewater. So a larger amount of solids would equate to a larger amount of bacteria that are in the system. Now, for the treatment plants that are lacking in space, we can actually replace the secondary clarifier with a membrane technology. That is called the membrane bioreactor. Instead of a clarifier, a membrane module separates the biosolids from the water after aeration. This is an example of a membrane bioreactor. So in just one small tank, we can accomplish both aeration and the solid-liquid separation of the sludge with the clear water at the same time. This results to a faster and more efficient process in removing BOD, total suspended solids, ammonia, phosphate, and coliform bacteria. The only downside to this process is sometimes membranes can be quite expensive and they can be quite short-lived because they are easily fouled and clogged. However, with the rapid development of technology, we can hope that one day we can have membranes that are less susceptible to fouling and clogging. Another type of bioreactors for the secondary treatment process is called attached growth bioreactors. In the previous cases, for the suspended growth bioreactors, the bacteria are residing at the surface of the solids present in the wastewater. For attached growth bioreactors, the bacteria responsible for treatments are grown on media with a high specific surface area, and then the wastewater is made to contact the media. This typically use less energy compared to the suspended growth reactors because the pumping of air in the suspended growth bioreactors is very energy intensive. An example of an attached growth bioreactor are trickling filters. Here is an example of a trickling filter. We have influent wastewater is made to trickle down a column of porous media. A higher specific surface area means that more bacteria will degrade the organic matter. In the trickling filter, we have an inert media, typically plastic particles, rock particles, or sometimes even slag, and that media creates an environment wherein the water is contacted with a large amount of air. Therefore, we call this a passive oxygenation process. It is a highly oxygenated environment that does not require active aeration, meaning our energy use is not being spent in diffusing oxygen into the water. All we have to do is to pump the wastewater at the top of the trickling filter, distribute it evenly, and as the wastewater trickles down that tower, it gets into contact with oxygen and also with the bacteria that degrades the organic matter. In theory, the effluent of the trickling filter is already clean and contains less organic compounds. These types of filters are of great use in aquaculture systems wherein the main goal is to introduce oxygen in the water as well as to convert ammonia to nitrates. Ammonia being converted to nitrates requires oxygen, and a trickling filter provides large amounts of oxygen to the process. Another type of attached growth bioreactors are what we call RBCs or rotating biological contactors. This is an example of an RBC. You can see that this is a large drum with materials that are inducive to the growth of microorganisms. This is a slowly rotating disc containing a large specific surface area favorable for housing a large amount of microorganisms that is contacted with the wastewater. So basically, a certain portion of this RBC is submerged into wastewater while the other portions are exposed to air. The concept here is, as the RBC slowly rotates, some parts of the RBC are exposed to the nutrient-rich wastewater, which the bacteria are feeding on, and some parts are exposed to the air, which oxygenate the water. Normally, RBCs are a combination of passive and active aeration. The passive aeration is coming from the exposure of the RBC to the air, while the active aeration is supplemental, and that is achieved by placing aerators at the bottom of the tank of the RBC. RBCs are still common in small-scale wastewater treatment plants that cater to municipal wastewater. Another type of attached growth systems are packed bed or fluidized bed bioreactors. In these types of reactors, we can achieve a combination of attached growth and suspended growth. Attached growth is coming from the media present inside of the packed bed or fluidized bed, while suspended growth is achieved by the presence of the biosolids or other suspended solids that are trapped inside of the bioreactor. If we introduce low fluid velocities, we have a packed bed. If our fluid velocities are sufficiently low, we have a packed bed wherein the media is stationary. However, if you increase the velocity of your influence, we can have fluidization or the media in the packed bed starts to move and we now have a fluidized bed. This type of system functions in the same way as MBRs or membrane bioreactor. We are accomplishing the aeration and the filtration on the same step. We are accomplishing the aeration and the filtration on the same step. Although this is less efficient because it can only filter large particles, while the smaller particles would still go through the bioreactor. Next, we have the tertiary treatments. So again, as a recap, for primary treatments, our main goal is to remove some of the physical properties of wastewater. Those are solids, turbidity, color, etc. For the secondary treatments, our main focus is the removal of organic matter. For the tertiary treatments, the focus is nutrient removal. As mentioned earlier, nitrogen and phosphorus are potent inducers of eutrophication. As such, they are addressed in the tertiary treatment, especially for wastewaters with elevated levels of nitrogen and phosphorus. Treated water destined to be used for crop irrigation may not need tertiary treatment. That's because we actually need those nutrients in the effluent water if it's going to be used to water crops. Most of the phosphorus is removed as part of the sludge after the secondary treatment. That's because organic phosphorus in the system tends to stick with the biosolids. However, most of the nitrogen is present as stable nitrate, which is very water soluble, as a result of oxidation in the secondary treatment. Therefore, we should expect that the nutrient removal process would focus mainly on the removal of nitrogen in the form of nitrates in the effluent water. One way of doing that is through the use of denitrification. If you go back to the biological process, we are introducing air such that the dissolved oxygen can be utilized by bacteria to degrade organic matter. A beneficial byproduct of that is what we call nitrification. That is the process wherein ammonia, which is very toxic, is converted to nitrates, which is relatively less toxic. Therefore, nitrate is largely formed in the secondary treatment. However, as mentioned, nitrate is stable and is very water soluble, and we still have to remove it from our water. That's why we have denitrification. Denitrification refers to the removal of nitrate through an anaerobic process. If the secondary treatment process is largely aerobic, the denitrification is anaerobic, meaning that oxygen should not be present in the process. Nitrification needs oxygen. Nitrification is the conversion from ammonia to nitrates, while denitrification needs the absence of oxygen. This incompatibility presents a challenge to the design of treatment systems. We have here an example of a denitrification system that is coupled with a secondary treatment system. If you take a look here, we have an anoxic denitrification zone, and then an aerobic nitrification zone, and then back to an anoxic zone and aerobic zone. This alternation of anoxic and aerobic zones facilitate the conversion from ammonia to nitrates and nitrates to nitrogen gas. Nitrogen gas is the final product of the denitrification process. The denitrification process also consumes carbon-based compounds or organic compounds. That's why in some cases, denitrification is coupled with the secondary treatment process. Now finally, after all of those steps, we now arrive at the disinfection step. Before the effluent water is released, it is disinfected to eliminate pathogens. At this point in the wastewater treatment process, we should have already removed all of the settleable solids. We should have removed majority of the organic compounds such that we would have a low BOD. And we should have also removed majority of the nutrients through the tertiary process. What's only left in the water are bacteria, the bacteria coming from the secondary process. Before releasing that effluent to any body of water, we must kill all of those bacteria. That disinfection is done by contacting the clean water with disinfectants such as chlorine gas, chlorine dioxide, hypochlorite, ozone, and UV irradiation. The choice of the disinfectants would vary depending on the process or depending on the availability of the disinfectants. After the step of disinfection, technically we now have treated wastewater. That treated wastewater can now be released safely to the environment. However, the wastewater treatment process does not end with the release of clean effluent. So after we have cleaned the wastewater, and after we have released the treated wastewater, it is now time to face the waste that we have generated in the entire treatment process. And that waste is called the sludge. If you notice, on every step of the process, we are generating sludge because the sludge is mainly the thing in the wastewater that we don't want in our water. This includes the grit, this includes the settled solids, this includes organic matter, and other substances that have been separated from the water. Therefore, sludge handling and treatments are vital parts of the wastewater treatment paradigm. One of the most common types of treatment for sludge handling is called anaerobic digestion. This is the most common method employed for sludge stabilization. In anaerobic digestion, the sludge is kept in anaerobic conditions to facilitate methanogenesis through the breakdown of organic matter. Simply saying, we are further degrading the sludge or the organic matter in the sludge by the use of anaerobic bacteria which turns the organic compounds into methane. Methane, being one of the primary outputs of anaerobic digestion, can be used as a source of fuel. We can burn methane to generate energy. Another output to the anaerobic digestion process is a slurry of digested sludge. This digested sludge commonly contains compounds that cannot be broken down by bacteria. So what do we do with our digested sludge? We perform dewatering. Dewatering is done to reduce the moisture content of digested sludge before we dispose the digested sludge. And the cheapest way to do this is to dry the settled sludge in open ponds, such as what is pictured here. Now, this is the simplest process of dewatering digested sludge. However, it is also the most time-consuming process because it takes a very long time for us to remove most of the water in the sludge. This process typically takes 3 months or sometimes even more. So for those treatment facilities that lack the space, we can resort to other dewatering technologies. Other mechanical processes that can be employed to hasten the dewatering process are using filter press and centrifuge. A filter press simply filters out the solids and separates them from the liquid, while the centrifuge utilizes centrifugal forces to force the settling of suspended particles in the sludge. After we have dewatered the sludge, it is now time for the disposal of the sludge. Dried sludge or biosolids are utilized differently depending on the country, region, and preferences. It also depends on the influence of the wastewater treatment system. If the influence is known to contain hazardous substances, then it would be best that the sludge be disposed in landfills. If the influent to the treatment process are largely of biological origin, such as human waste, we can apply the dewatered sludge to agricultural soil as a conditioner. This is one way of returning the nutrients back into the soil. We can also compost to further break down the organic matter present in the dewatered sludge. Remember, the components of the dewatered sludge are now the substances that cannot be broken down by aerobic bacteria in the secondary treatment process and by anaerobic bacteria in the anaerobic digestion process. So composting could help further break down the organic matter present. In some countries, the dried sludge is incinerated to recover energy. This is done in conjunction with the combustion of methane generated from the anaerobic digestion. The generated energy from incineration and from the burning of the methane can be used to power the wastewater treatment plant itself. Now that we have discussed the conventional wastewater treatment system, let us now discuss some other technologies for wastewater treatment. Always keep in mind that we are not limited to the conventional way of treating wastewater. We have here some innovative and some emerging technologies for the treatment of wastewater. First, let us discuss struvite precipitation. Struvites, or magnesium ammonium phosphate, is a mineral that can be precipitated from wastewater as a form of nutrient recovery. If you take a look at the chemical composition of struvites, it contains nitrogen, magnesium, and phosphorus, three elements that are vital to the growth of plants. Also, nitrogen and phosphorus are common in wastewater. Struvite is valued as a slow-release fertilizer. And struvite is better precipitated from collected urine, or what we call yellow water, that is separate from black water. That is because black water contains many substances that can hinder the formation of struvite. This is an example of a process that precipitates struvite. This process involves the addition of magnesium because struvite contains magnesium. If we are sacrificing magnesium into the solution, that forces the nitrogen and phosphorus in the wastewater to combine with it to let struvite precipitate. There have been many studies involving the optimization of the precipitation of struvite, and we are hoping that in the future, struvite precipitation will be a normal part of the wastewater treatment process. Another treatment technology that is worth noting are constructed wetlands. A constructed wetland is a biologically active system that naturally cleans wastewater from the combined action of plants and microorganisms. This is an illustration of a constructed wetland. Basically, it's a depression in the natural soil that is lined with a non-permeable material such as clay or a polymer lining that prevents the wastewater from seeping into the ground and affecting our groundwater. Natural flow can be adopted to induce a slow flow through inert media, typically that is sand and gravel, with wetland plants that harbor beneficial microorganisms in their root zones. Basically, we are combining the treating action of the plants, normally they are wetland plants, and the bacteria that are residing on the roots of the plants. This is a biological treatment process that utilizes a very small amount of energy. All we have to do is to provide the energy needed for pumping the wastewater through the constructed wetland system. We can even design the constructed wetland to not use pumps at all. We can use gravity flow and other technologies to redirect the flow of wastewater into the constructed wetland. Now, since this is a biological process, we expect that constructed wetlands are slow in treating wastewater. But this gives us a low input alternative for the conventional treatment of wastewater. Next, we have electrocoagulation. Electrocoagulation is the application of electricity through iron or aluminum electrodes to induce a redox reaction that releases metal ions into the wastewater. Electrocoagulation is an emerging technology that promises a one-step process in wastewater treatments. Basically, we simply have to apply electricity on two electrodes. Normally, these are iron or aluminum electrodes, and that results to the release of hydroxide ions and metal ions. The metal ions are responsible for binding with the hydroxide ions as well as the other organic substances present in the water. This process greatly accelerates coagulation, therefore enhancing the separation between the clean water and the sludge. If developed properly, we can use electrocoagulation to replace the entire conventional wastewater treatment system. All we have to do is to think of a scheme that uses renewable energy sources as the source of electricity for the electrocoagulation. The number one disadvantage of an electrocoagulation system is the electrodes are being consumed. Therefore, you are introducing metal ions into the water. Further development of this technology could help it become a staple in wastewater treatment. And finally, we have microbial fuel cells. Microbial fuel cells utilize bacteria to consume the organic substances in wastewater while generating electricity in the process. The net effect is the reduction of organic substances in the wastewater and the generation of electricity. The generated electricity can be used to power the wastewater treatment plant. Microbial fuel cells are a novel concept that utilizes the same bacteria in the secondary treatment process of the conventional wastewater treatments, but now we are separating the chamber into two. We have an anodic chamber and a cathodic chamber. The anodic chamber is anaerobic, while the cathodic chamber is aerobic, and that separation makes this some kind of a battery wherein the bacteria are the main workforce of the battery. The bacteria simply consumes the organic compounds, they metabolize the organic compounds and form carbon dioxide and water, and in the process, they also release electrons. Those electrons can be captured by electrodes and we can generate electricity. As of now, microbial fuel cells are proven and tested in small-scale systems only, and they are yet to be employed in the commercial treatment of wastewater. Although it is our hope that in the future, microbial fuel cells could provide both a renewable energy source and a sustainable way of treating wastewater. There are many other kinds of emerging technologies that has the potential to greatly enhance our treatment of wastewater. Those technologies will be left for the students to research. In the end, we are utilizing our knowledge of wastewater characteristics and the wastewater treatment process to safely and efficiently treat wastewater so that our effluents will not be harming the environment. That's it for this lesson. Thank you for listening, and as always, keep safe.